I am Pocho Salcedo, and I welcome our audience in South America and those who join us from coast to coast in the United States of America, Hawaii, and Puerto Rico. Once again, inviting you from New York to a walk beyond the headlines. Welcome to the DNA of the news. Today, we will talk to a personality in the world of space exploration. He has dedicated much of his life to the Voyager 1 and Voyager 2 programs. These spaceships have been traveling in space for almost 45 years at the speed of 540 million kilometers per year. They are the first objects of our civilization that have entered interstellar space. Still, it is estimated that between 14,000 to 20,000 years or more, they will leave the confines of our solar system in our galaxy. Let us recall there are an estimated 100 billion other galaxies. This is the story. Dr. Ralph McNutt joins us from Laurel, Maryland. Dr. McNutt, welcome to the DNA of the news.
Thank you.
Ralph McNutt Jr. is a physicist and member of the principal professional staff in the space exploration sector of the Johns Hopkins Applied Physics Laboratory. He received his B.S. in physics at Texas A&M University and his Ph.D. in physics at the Massachusetts Institute of Technology in 1980. Dr. McNutt is currently as a co-investigator on NASA's Voyager, New Horizons, and Parker Solar Probe operating missions and on NASA's Europa Clipper, now under development. He is an author on over 220 papers and co-chaired National Academy's studies on radioisotope power systems and NASA's large strategic science missions. He is the principal investigator on the recent study of a pragmatic interstellar probe mission for NASA's Heliophysics Division. He is a member and trustee of the International Academy of Astronautics. He is a recipient of many awards in his scientific career. Minor Planet 172,191 Ralph McNutt is named for him.
Well, let us start at the beginning. In the summer of 1997, NASA's Jet Propulsion Laboratory launched Voyager 1 and 2, a 5-year mission to study Jupiter and Saturn and their moons. 45 years later, NASA is still in communication with both probes, now in interstellar space. How did the longest running mission in the history of space exploration come about? You were at the launch site on one of those dates.
Right. I was at the Voyager 1 launch, which was on the 5th of September of 1977. Voyager 2 had actually launched earlier on the 20th of August. So Voyager 2 launched first, Voyager 1 launched second. It was just the beginning of a lot of the details of the mission. But no, I was a graduate student at MIT, and was with the science team. The team that I was with had one of the instruments on board, and I'm still a member of that science team and a member of another one of the science teams as well. And so I've been watching Voyager while Voyager has been watching a lot of things out there as it's been crossing the solar system. And we were originally built to get to Jupiter and to get to Saturn. Actually, the whole idea behind Voyager was due to a student named Gary Flandreau, who was studying solar system dynamics in the early 1960s and realized that if you launched a spacecraft in the late 1970s, you could go by Jupiter, close enough that the gravitational force would change the direction of the spacecraft and make it go faster, and then go by Saturn, and then go by Uranus, and then actually reach Neptune in something like only 14 years, which otherwise would take about 40 years to do. And so this was it's a unique opportunity. It only happens about once every 174 years. And it was just at the right time to be doing the engineering up front. And so this had been really the culmination of a huge amount of engineering work in order to fly out of the solar system. And originally, the amount of money that was available was cut back to only allow the spacecraft to go to Jupiter and to Saturn. And then the mission was going to be over. And they've launched 2 because they were afraid they might lose 1. And this is how things used to be done in order to guarantee mission success. And so what's happened is that we've been able to convince the science community and NASA and the U.S. Congress that pays for the bills via the American taxpayers to keep extending the mission and to go ahead and actually do the flight to Uranus and the flight to Neptune, and then keep extending the mission out to where it is now, well beyond the magnetic field of the sun out in the nearby interstellar medium.
Thank you very much for the background. The news is that Voyager 1 and 2 have now traveled 22 billion kilometers. It's tough to imagine it left the heliosphere and entered interstellar space. What does it mean?
Well, we had always suspected that, we knew that at some point the extent of the sun had to end in terms of what we see now in the nearby interplanetary space. We've known from the early 1960s that there's something called the solar wind, which is a flow of material that is always coming out from the sun. It comes out in all directions. It's supersonic. It was predicted by Eugene Parker when he was an assistant professor at the University of Chicago in the late 1950s. Was confirmed by the Mariner 2 spacecraft in 1962 when it was en route to Venus. And it's still something that we're investigating right now with the Parker Solar Probe mission. But we knew that at some point there had to be a place where the solar wind carrying the sun's magnetic field with it would run into the interstellar medium, and there had to be a shock wave that was set up, sort of like around the front of the bow of a boat going through the water. And there had to be this interaction, and then with interstellar space on the other side. The only question was nobody knew exactly how far that extent was, because it depended upon the conditions in the interstellar medium, and we didn't know what those were either. And so it's only been with the Voyagers that we've actually discovered where those boundaries are, and the fact that we've now passed them with both Voyager 1 and Voyager 2.
Talk to us a little about what goes on among the NASA scientists and mission control. For example, when Voyager 1 crossed the heliopause and entered interstellar space, the organization and NASA waited nearly 1 year until it announced, because the models predicted did not reflect what the instruments were reading. Then I think Voyager 2 came and did the same thing, and then it was a confirmation. How are those internal discussions take place, and the announcement of this momentous occasion took almost 1 year?
Well, that's right, because one of the things about science is you want to be correct, and you want to be right, and you want to be as descriptive as possible, with the answers. And this was such a long-awaited question about where this boundary was. Everybody wanted to be sure that the analysis was correct and everything made sense. And of course, the thing is, the models that we had, and people have been working on the models for the mathematical models for a long time, they don't really fit the observations as well as everybody thought that they would. And so that was the reason for a lot of the consternation and a lot of the waiting. There were a lot of arguments back and forth. We know from the interaction of the solar wind with the magnetic fields of the other planets in the solar system that there's sometimes what are called boundary layers. In other words, that's not such a sharp crossing of the heliopause as that one might have thought. There might have been a different set of particles, and we'd just gone into a different regime, and we weren't really in interstellar space. As a matter of fact, there's a couple of people that are associated with Voyager that still think that the rest of us have it wrong, and that we are actually still within part of the extent of the so-called heliosheath. That's the region inside of the heliopause. But they're currently in the minority, but we shall see. And so we also had several of the instruments are making measurements that they just weren't designed to make it at all. I mean, the plasma instrument that looks at sort of the low temperature part of the charged gas that's out there, the plasma, it's called plasma. The one on Voyager 1 is broken. It's been broken ever since the Saturn flyby, so it wasn't working. The one on Voyager 2 is just barely above noise levels out there because it was not designed to be running at those kinds of low levels in terms of the density of the material. We have magnetometers on both of the spacecraft, but they also weren't designed to be measuring magnetic fields as small as that they are, and so it's been very hard to actually tease out the real signal.
Look, I always wonder, and you were quoted saying, talking about the Voyager probes, so we have done 10 times the warranty on the darn things. My question is, was this an outcome, an accident or laborious work over design, work of the engineers to deal with all the contingencies? What are your thoughts?
Well, it's a little bit of both. You know, when I was growing up, my dad always told me that if you had your choice between being smart and being lucky, choose lucky. And we've been extremely lucky with the Voyagers. I mean, at the time, one has to remember that at the time when these were built, spacecraft didn't necessarily last that long because we were really still trying to understand how that the electronics could fail in the radiation environment. Just aging of the electronics. I mean, there are a lot of just discrete transistors, for example, that are on Voyager. The Voyager memories are something like 1/1000th the size of the memory that's in an iPhone today. I mean, by current standards, these were very, very primitive constructs. And so one of the things that you do is you very carefully look at all of the electronic parts that go into the electronics. You look at all of the other parts and you try to figure out what you need to test, how much you need to test, try to decide what might enable you to predict that the lifetimes would be long. Again, the design point was 4.5 years. There were instructions to the engineers not to preclude anything that would cause an end of the spacecraft life before 7, but a lot of it was just we just got very, very lucky, and we've had an incredible crew of people who have been dedicated to running these spacecraft out at the Jet Propulsion Laboratory for all of these years, and an incredible crew of scientists that did a really good job in building the instruments. But you know, never turn down luck. It's always a good thing to have on your side.
Well, from what we have read, it will take 14 to 20,000 years for Voyager to emerge from the Oort cloud, which shows how vast the universe is. Is the Voyager going to outlast even planet Earth?
Well, it could. I mean, it's not going to be still sending messages back to us, because right now the limitation on the spacecraft is the power supply, which is driven by an isotope of the element plutonium. It's plutonium-238. It's something that we actually make here on the Earth. It's been used as sort of a space battery, or the component of a space battery, since 1960 with the launch of Transit 4A, which was an Earth orbiting satellite. We've gotten better and better about knowing how to build these. At the time that the Voyagers were launched, we had a power supply output of about running at around 400 watts of electricity on each of the spacecraft. So you could think about, you know, a couple of tabletop lights that you'd put at each end of your sofa. And that's how much power we launched with. We are down now to about half of that amount because of both the decay of the isotope, which plutonium-238, which provides the power, as well as the aging of the converters, which change what's essentially heat coming out of these batteries into electricity, tying everybody that's still associated with the spacecraft together. And we've been going over with the engineers and with the program manager what needs to be done to try to extend the lifetime and the distance that we can get data back as far as we possibly can. And so that's currently one of the things that's uppermost in everybody's mind. But that is what basically sets the limit, is how much electrical power.
And we will be right back, and we will pick from this exciting technology discussion and how Earth communicates and receives data from the Voyager probes. It is a fascinating story. Before the break, we were talking about communication that is two-way. From what we understand, 21 days going at the speed of light is what it takes to connect with the probes. Tell us about the antennas of the Deep Space Network. What are they like? I was surprised to learn that, for comparison, a modern-day digital watch has billions of times more power than the signal coming in from Voyager 1 and 2. And for us humans, sometimes it is hard to communicate via cell phone across town. Please put us in the spectrum of how you see communications.
Sure. Well, let me just mention. So we're not 21 days out yet. We eventually will be, but we won't be hearing back to the spacecraft. We're actually at about 24. It takes about 24 hours right now to get
24 hours.
24 hours to get a signal from Voyager 1, which is the furthest out, back to the Earth. That translates into about 155 AU, or astronomical units, and this is what all of us nerds use. So 1 AU is the distance from the Earth to the Sun. So that's about 93 million miles, or about 147 million kilometers. So you multiply that by about a little over 150, and that's how far we are out, which is about one light day, okay, because it's the distance that a light can travel in a day. So you can compare that with the distance to the nearest star, Alpha Centauri, which is about 4.3 light years. So wow. Stars are a long way apart, but nonetheless, with Voyager right now, we've got the transmitter on board uses part of the energy that comes out of the power supply. It's providing it's around 20 watts of electricity. So think of a very, very dim light bulb, and that's what's going into an antenna that's got a parabolic shape. It's 3.6 meters in diameter. That's aimed back at the Earth. And so a little over a day after transmitting, the signal is received at one of the receiving stations of what's called the Deep Space Network. We actually have 3 of these complexes. One is outside of Goldstone, California. One is in Canberra, outside of Canberra, Australia, and one is outside of Madrid, Spain. And each of these have a main receiver, which is steerable, looks like a radio telescope. It's a steerable antenna, 70 meters in diameter. There are also, at least at Goldstone, and I don't know about the other 2, they've been upgrading the stations to also include 3 additional receivers, which are 35 meters in diameter. And usually the Voyager signal comes in to the main 70-meter diameter dish. We can electronically connect it along with the other 3 dishes together in order to increase the reception rate. But right now, typically the spacecraft is tracked each one is tracked about 5 days a week. We get a data rate of about 160 bits per second. So, it would take a long time to download a movie at 160 bits per second. You really wouldn't like the experience. But nonetheless, that's what we can do from these distances. It is really, it's an amazing thing to see how that all of this has come together. And it's really a technological tour de force that we're able to actually pick up the spacecraft that far away.
Well, there are so many things inside this program that probably makes this journey even more interesting when you are in the day-to-day with the Voyager program. Still, one of the issues that makes me think mm, all the time is this famous pale blue dot photograph of Earth at a distance of 6 billion kilometers. If I understand correctly, a gentleman named Carl Sagan lobbied to convince NASA to take those pictures. At the very least, it seems this was a public relations success that NASA should have embraced in the beginning. Still, there was intense discussion to turn Voyager and take pictures, perhaps one of the last pictures taken. Tell us how those issues are dealt with within the scientific community.
Well, you're quite correct. That was so the family portrait, which was a portrait of all of the planets from Voyager, was indeed the last set of photographs that were taken. There were actually several that were taken for both the wide angle and the narrow angle cameras. And yes, Carl Sagan had to lobby quite a bit to colleagues to say, you know, we really need to do this. And all the scientists said, yes, this sounds like a really good thing to do. And most of the engineers said, why are we doing this? This is just one more thing for us to have to worry about. And we don't like extra things to worry about. But you know, it took a little bit of discussion. But I think, you know, everybody finally came around to the idea that, well, you know, this was a unique opportunity because we'd never had a spacecraft with that good of a camera that far away before. Pioneer 10 and 11, which were also escaping from the sun, they were spinning spacecraft. They were launched in 1972 and 73 and got by Jupiter and Saturn. The cameras were not that good, and they also fell silent because their power supplies had decayed. So Voyager 1 was sort of the first time that you actually had the photographer in the right place to be able to do a family portrait with everyone smiling and with the Earth being its little blue self, and being able to be seen, and you know, and hence the moniker, the pale blue dot. And you know, all of a sudden, it was a way of actually illustrating that it's a really big universe out there, and this planet that we all live on is not that big by comparison. And so it's, you know, it's a question of perspective, and I think a question of you know, kind of educating people about what our home really looks like, and giving us all a better appreciation for the fact that we better take care of the place.
Well, please tell us what Voyager 1 and 2 have taught us about how big the universe is. We know how far they have traveled, but this is only within our galaxy. There are billions of galaxies, if I am correct. How can we understand, and how do you scientists deal with that?
Well, you know, I think that for those in the audience who've read The Hitchhiker's Guide to the Galaxy, there's a line in that about space is big. It's really big. And you know, that was kind of, I think that's kind of been the best explanation that I've seen. I mean, you know, we talk about the fact that the nearest star, Alpha Centauri, is about its star system. Actually, there's three stars that are gravitationally bound together, about 4.3 light years away. So, if you sort of reverse engineer this, one light year, the distance that light travels in a year, is about, I mentioned AU, astronomical units, before. One light year is about 62,000 astronomical units. Okay, so that's about the location of the center of the so-called Oort cloud of comets, which are the really long period comets that are coming in from the extent of the sun's very weak gravitational pull. It's about 1 AU is where the pull of the other stars sort of start taking over in the near solar neighborhood. And so we ourselves are located several thousand astronomical units from the center of the Milky Way galaxy. We're actually out in the boondocks. We're out in the neighborhood, a long way away from downtown. And then, of course, the Milky Way and several other galaxies are in what are called the local group. That then extends to part of the local supercluster. And as, of course, as we've now been seeing with these spectacular new photographs from the James Webb Space Telescope, that there really are a lot of galaxies out there. I mean, it's been said before that there are more galaxies in the universe than there are grains of sand on the beach, and of any beach you want to talk about, or even all of the beaches on Earth. And it's no understatement. So again, trying to wrap your head around, the immensity of these numbers is something that's very, very hard to do. I think even for those of us who've been trying to do it for a very, very long number of years now. But again, it's a question of trying to, trying to educate ourselves, and I think trying to educate all of our fellow human beings on this planet that what that the universe really does look like, and we are perhaps a small part of it, but we are all a part of it nonetheless.
Ralph, I have a question for you in the last few seconds we have left. What do you wish you knew at the beginning of your journey as a scientist that you know now that you wish you knew 20, 30 years ago, or when you started with Voyager program, or any other project like that?
Well, that's a good question. My first inclination would be to say that, I wish I knew better that, it's not so easy to do this stuff. But on the other hand, if I did know that, I might not have started any of this either. So I'm not quite sure what that the correct answer is, I'm afraid.
Thank you very much. It has been an honor and a pleasure to have you on the show. We will keep following this and we invite our audience to follow the conferences and your writings. You have a way of explaining complex issues that we can all understand. Thank you very much.
Well, thank you. Thank you for the opportunity, and thanks to the audience for listening.
Thank you for allowing us to be part of your day. Until the next opportunity, we present another edition of the DNA of the News from New York for your kind consideration.